Hi everyone. I introduced you scenario benchmark of AIBench about, and now I'll introduce you the Edge AIBench towards comprehensive end-to-end AI edge computing benchmarking, a part of scenario benchmarks. Now, this is the outline today. I'll introduce the background first. By 2025, forecasts suggest that there will be more than 75 billion Internet of Things connected devices in use. With the explosive growth of those client-side devices, the data produced by these devices will be enormous, which makes conventional cloud computing not efficient enough to handle all this data. What's more, using the cloud as a centralized server simply increases the frequency of communication. This figure shows the architecture of edge cloud computing in a distributed cloud environment. We can see the magnitude of devices from each layer. If we put the most of computing tasks on cloud layer, the overhead of data transmission and data encryption among devices and data centers become significant bottlenecks. Therefore, it raises a daunting challenge for cloud computing with throughput, latency, security guarantee, energy consumption, and so on. Therefore, edge computing architecture emerges as a promising technical framework to overcome the challenges above in cloud computing. The edge computing framework adds a new layer, named the edge computing layer. On the basis of the traditional cloud computing framework, this figure shows a general edge computing framework, which includes 3 layers: cloud server, edge computing layer, and client-side devices. Edge computing is a new distributed computing paradigm which moves the computation away from data centers and bring the computation and data storage closer to users, so it can improve the response time and save the network bandwidth. Edge computing decentralizes traditional cloud computing to alleviate problems associated with limited bandwidth, latency, and data storage in centralized cloud computing. Moreover, artificial intelligence technology is now widely adopted in edge computing, such as augmented reality, smart city, healthcare, wearable devices, and so on. We simply refer to those edge computing scenarios using AI technical edge AI. There exists a wide range of edge AI scenarios and applications. Edge AI has been identified by Gartner Research as a new thrust of research and development in 2020. However, Edge AI is in the initial stage and doesn't have a uniform standard for those scenarios. Therefore, a benchmark rate for Edge AI applications is needed to measure the performance and help to optimize the framework and applications. But there are many challenges for the Edge AI. These edge AI scenarios are complicated because of the 3-layer AI edge computing architecture. The evaluation processing need to cover the overall architecture and the critical path. Moreover, there are many challenges for edge AI benchmarking, such as how to reflect the 3-layer collaboration, considering the critical paths and primary models. So an end-to-end benchmark is needed. And for Edge AI benchmarking, how to reflect the diversity and complexity is also a problem. Because of the different kinds of client-side devices, a large quantity of heterogeneous data, privacy, and security issues, most of those scenarios have a high requirement for latency and network bandwidth. Although edge computing solves many problems of centralized cloud computing, it also have many challenges because of its complicated scenarios. Based on our extensive survey, we conclude 6 significant characteristics of edge AI scenarios. This slide shows those 6 properties in specific scenarios. The first one is high accuracy, because some edge computing scenarios need reliability due to their particularity, such as autonomous vehicles. Various tasks have different requirements for accuracy. We take an autonomous vehicle as an example. The accuracy of those tasks even need to be close to 100%. Nevertheless, for ICU Patient Monitor, accuracy is not the most important thing to be considered. In our survey, the state-of-the-art algorithms of those scenarios still lack precision. The second one is latency tolerance. Actually, most of the edge AI scenarios have high real-time demands as they are closely tied to human life. For autonomous vehicles, due to their network condition methods, the communication latency can be up to 10 milliseconds using 5G technology. Moreover, the total end-to-end execution time latency can be up to 100 milliseconds. The third property is mobile. Mobile means that end devices are not static in one place. Mobile edge computing is a crucial technology and architectural concept in edge computing. And the fourth property is multiple users. Usually, one edge server needs to correspond with multiple users, such as ICU Patient Monitor scenario. One edge server corresponds to multiple patients. In the surveillance camera scenario, one edge server corresponds to multiple cameras. In the smart home scenario, one edge server corresponds to various devices. However, one AI chip can serve one smart car due to the particularity of the autonomous vehicle. The fifth property is enormous data. As HRS Market reported, 1 billion surveillance cameras will be watching around the world in 2021. Moreover, it has been calculated that 24 hours of 4K 60 FPS videos take nearly 35 terabytes storage. Therefore, there are enormous data in edge AI scenarios. And the next property is heterogeneous devices and data. In edge computing scenarios such as smart home, there are multiple heterogeneous devices, including smartphone, computer, iPad, router, camera, and so on. That's how to processing those data is also a problem need us to solve in edge AI scenarios. In our BenchCouncil AI bench system, we propose a scenario benchmark, and I have introduced it. So we think scenario benchmark is needed And a scenario benchmark is a proxy of a realistic application scenario and a permutation of a series of AI and non-AI components to capture the critical paths and primary modules. Therefore, we propose Edge AIBench as a scenario benchmark to answer the question and present the 6 properties of Edge AI scenarios. Next, I'll introduce Edge AIBench. Based on the above requirements, we propose a scenario-based benchmark suite named Edge AIBench for Edge AI computing scenarios. Edge AIBench concentrates on the edge computing artificial intelligence. It's the first comprehensive end-to-end Edge AI benchmarking framework, and Edge AIBench takes an end-to-end view and divides the task into 3 parts: cloud server, edge computing layer, and client-side devices. And the Edge AIBench is a scenario-based benchmark, and more information is available on BenchCouncil Edge AIBench website here. And additionally, there are our applications based on Edge AIBench. In the previous page, we mentioned that Edge AIBench takes an end-to-end view. So what is end-to-end? Actually, there are some work about edge computing benchmarking, but they all focus on one layer, such as inference on edge computing devices. In the edge computing scenarios, the distribution of data and the collaboration of workloads on different layers are serious concerns for performance, security, and privacy issues. So for benchmarking, design, and implementing edge computing systems or applications, we should take an end-to-end view, considering all 3 layers and their collaboration. And this figure shows the critical path of an AI task in Edge AI architecture. We can find that both training, processing, and inference need to be considered in an Edge AI benchmarking. When put those processing tasks on different layers, performance will be influenced deeply by diverse workload and data allocation in 3-layer edge computing architecture, as some edge or end devices cannot support the complicated AI computing tasks. Collaborating needs to be considered among cloud, edge, and end devices. Therefore, the performance evaluation and analysis needs to cover the critical path. Edge AIBench follows the PRDAERS benchmarking rules and methodology presented by BenchCouncil. The PRDAERS is the abbreviation of paper and pencil, relevant diversity, abstractions, evaluation metrics, and methodology, repeatable and scalable. This figure presents the constructions methodology of our Edge AIBench. Firstly, the typical scenarios are extracted to present the numerous Edge AI scenarios, and then the primary layers with macro components and application benchmarks are extracted. In addition, the heterogeneous representative real-world data sets are chosen as the dataset. To organize our benchmark suite, we adopt a scenario-based benchmark view. The scenario benchmark idea means extracting primary scenarios which can represent the characteristics. Also, those scenarios need to cover all applications complexity in edge computing. Edge AIBench considering all of the six scenarios characteristics and the typical applications. So we extract 4 typical scenarios which can present those characteristics: autonomous vehicle, ICU patient monitor, surveillance camera, and smart home. This figure shows our 4 scenarios in Edge AI environments. We think they can represent the complexity of edge computing. The first one is autonomous vehicles. Autonomous vehicles requires a real-time response. The automatic control system needs to analyze the current road conditions and make a corresponding reaction at once. In the 6G environment, the communication latency can achieve 10 milliseconds, and the end-to-end latency needs to be reached 100 milliseconds. The accuracy of those tasks even needs to be close to 100% accuracy. The uniqueness of autonomous vehicle scenario is that the high demand for the accuracy. That is to say, it needs to take absolute correct action even without human intervention. Autonomous vehicle is a typical scenario using mobile edge computing technology because the car is mobile. Linking. In autonomous vehicle, we choose 2 tasks: lane detection and road sign regulation. Lane keeping is one of the most important parts in autonomous vehicle scenario, helping autonomous cars in their proper road lanes. And for lane detection, we choose LaneNet and HNet as the network model and choose 2 simple data sets as the dataset. And this is our reported accuracy. And the next one is road sign regulation. Road sign regulation is a complicated autonomous vehicle application because of many of the constraints, such as brightness of the natural environments and the speed of the vehicle. Moreover, road sign regulation is also a very significant application and need a highly reliable results because it may cause the death on account of one wrong regulation of the road sign. And another thing need to be considered in this task is the sign's orientation, such as rotation, blurring, and the positioning of the sign in the different image. In this task, we choose capsule network as network and the German traffic sign regulation benchmark as the data size, and our reported accuracy is 97.6%. The second scenario we propose is ICU Patient Monitor. ICU is a treatment place for critical patients. Therefore, the fast response time is significant for ICU patient monitor scenario to notify doctors of the patient's status as soon as possible. Response latency is also very important in this scenario. As the wild network latency can reach 1 millisecond, the end-to-end latency can reach 10 milliseconds in this scenario. In the ICU patient monitor scenario, one edge server corresponds to multiple patients. That means the edge server needs to process multiple concurrent tasks at one time. In this scenario, we choose 3 tasks: heart failure prediction, decompensation prediction, and phenotype classification. Heart failure detection uses the information of the first 48 hours in ICU to predict the heart failure. It uses a 2-layer LSTM model. And this is our reported data. And the decompensation prediction also uses the LSTM model. And this is this task's information. And the phenotype classification also uses LSTM model, and this is information. And the third scenario is surveillance camera. As we mentioned before, the HIS market reported 1 billion surveillance cameras will be watching around the world in 2021. And it has been calculated that 24 hours of 4K, 60 FPS takes this huge, enormous data in surveillance camera. The property of this scenario is the enormous data. In this scenario, we choose two AI tasks. The first one is person identification. We choose the person identification aiming to establish identity correspondences across different joint cameras. For this task, we choose DGNet network as the network and choose the ResNet 50 pre-trained model, and we choose market 15.1 as the data size, and our reported accuracy is 94.8%. The second task in surveillance camera is action detection. Action detection is used to regularize the abnormal behavior in video surveillance. The task is quickly detected in a short time window. For this task, we choose ResNet 18 as the 3D model, and the UCF 101 as the data size, and the reported accuracy is 93.3%. And the last scenario is the smart home, because smart home scenario consists of many different devices, such as smartphone, camera, window, and so on. So it will produce heterogeneous data, such as text, image, audio, video, and so on. So this scenario can represent heterogeneous devices and data property. In this scenario, we choose two AI applications as the tasks, speech regulation and face regulation. These two components have heterogeneous data and different collecting devices. We use Deep Speech 2 and FaceNet as the model, Library Speech and LFW as the data sets. Okay, this table shows the 9 typical AI tasks in AIBench, and we have some components benchmarks of them. Edge AIBench provides an end-to-end scenario-based benchmarking consisting of training, inference, data collection, and other parts using a general 3-layer edge computing framework. And it has nine open source data size now. We also give the reference implementations of them, and open source code is available on our website. Because we give the reference implementations of the above Edge AI tasks, and the open source code is available on BenchHub here. Its current release is 1.0, and this is a web link. If you want to use Edge AIBench on your own machine, firstly, you need to prepare the environments of the selected software stack, because for one task, we may we may provide different implementations such as TensorFlow, PyTorch, and so on. Then you need to download the datasets as you need. Next, you can run the scripts or commands following README. We extract 9 real-world datasets for those 4 scenarios. This is part of their website links. You can download them in their website shows in this slide. We also conduct some experiments using Edge AIBench. We construct the experimental environment to simulate the realistic cloud edge computing scenario. Additionally, we assume that the cloud server has the highest computation ability. The edge server's performance is lower, and the end device's performance is the lowest. And meanwhile, the cloud server has a long distance to the end server than the edge server. This is our experimental environments. We use an AI-oriented Inspire cloud server as the cloud server, and Inspire edge server as the edge server without AI chips. And we choose Huawei Atlas 200DK as the edge server with AI chips. For user end devices, we choose Raspberry Pi 4B. This table shows their information. We choose 3 tasks from our Edge AI benchmark, and running the inference on our experimental environment. This figure shows the end-to-end inference latency of each application deploying on different layers using Edge AIBench application benchmark. From the figures, we can see that for different Edge AI tasks, the best execution layer for the shortest inference response time are different. Therefore, for the AI workload deployment on edge computing framework, different placement or collaboration policies in handling data size and workloads across cloud, edge, and the user and the devices may substantially affect the overall performance. Thus, we should take an scenario-based and an end-to-end view to construct the benchmarks. This figure shows the 3 different inference location methods on cloud server, edge server, and end devices, respectively. The problem is which layer to allocate the inference can get the minimum overall response time. So we perform a breakdown of each workload's end-to-end response time to processing time and transmission time across 3 layers. From this figure, we have the following observations. We can conclude that the more simplified the workload models are, the greater influence the transmission times has. Therefore, computing near the user may get the lowest response time. On contrary, for heavyweight workload being processed on higher layer may lead to the lowest response time. For the AI workload deployment on edge computing framework, we need to estimate the computation ability of the devices on different layers and the network condition firstly. Then we can decide which layer to put the workload on by trading off between the processing time and transmission time. Based on the above performance evaluation results and our evaluation results, we propose a QoS model for Edge AI devices. As this figure shows, we introduce a general Edge Edge Cloud AI performance model, we choose 4 representative Edge Cloud servers. Cloud server with GPU, Edge server with AI chips, Edge server without AI chips, and end device. Then we model them along different sets of performance metrics. This is the radar figure. Okay, let me conclude this presentation. In this talk, we introduce Edge AIBench, a scenario-based AI Edge computing benchmark suite with 4 typical scenarios and 9 Edge AI tasks and 9 real-world data sets. Moreover, we'll show how to use it next by my colleague Chuanxin Lan. Please refer to our website and the paper for more details. Thank you.